A horse walks into a bar and the bartender goes, why the long text? We're good. John, are you on?
Yep, I'm all set.
Great. Okay, so I want to introduce John Hall. He's an expert in infrared optical design. I was trying to remember when I met him. I went to work at Army Night Vision in 1997. And I'm pretty sure John was, it was about that time. If it wasn't too much different than that time that I met him. And he ended up being the best optical designer over my career that I had ever met. And I've always been a camera expert. I've not been an optical expert, but with infrared optics, which is, you know, mid-wave, long wave, that John was always the person I went and asked questions. And what about this? What about aberrations? What about F number? What? And he was always, and he has, had such a long career, and he's had quite a few proteges that have created companies, made big differences in the industry. He leaves a number of proteges that are quite capable, and he's trained a lot of these people to become experts himself. So he's really made an impact. He received his bachelor's from Rochester, his master's from George Mason, and he decided to finish up he's currently at Colorado State distance learning, finishing up his PhD. So with that, I'd like to introduce John Hall. John, we're grateful for you to give us this talk over distance. So John, it's all you now.
Okay, thank you, Ron. Hopefully my slides should be in the full screen mode. And we will get started. I am John Hall. I'm the what they call a subject matter expert for the U.S. Army at Fort Belvoir for night vision related optics and optical sciences. All right. And my screen just froze. Hold on here. Try that again. All right, looks like I lost control of full screen mode, so I'm going to keep it into, I think I'm going to have to leave it in this mode here. Hopefully everybody can still see. All right, so this lecture is aimed at an audience with a technical background. For those with optics backgrounds, I'm going to try and eventually get to some things that you probably have never seen before. And for those with just general engineering backgrounds, I'm also going to include a little bit of introductory matter just to make sure that the terms that I'm using are understandable. And to that end, we'll start with the first slide here is discussing the electromagnetic wave properties of light and the electromagnetic spectrum ranging from gamma rays, and then as you get into longer and longer wavelengths, it's out in the radio waves and beyond. And photons become more energetic when they have shorter wavelengths and higher frequencies. And they become less energetic at the longer wavelengths, of course. And I'm going to stick mostly with wavelength in my discussions of properties of light hereafter. So we'll keep it moving here and go to the next slide. So one good question a lot of people sometimes have in their mind already, they think they know where light comes from, but they may not really know. And so I've narrowed it down to these about 6 basic sources. Light waves are generated at the nuclear or subnuclear particle level, and we could consider every little atomic nucleus as a point source of light. And there are different types of atomic interactions which will cause the release of a photon, which is the most basic element of a light beam. So we have radioactive decay from a nuclear reaction. You can get light generated from nuclear fusion. There's also chemical reactions, photoelectric effects, which is how the principle of the light emitting diodes work, and excitations such as in the lasing medium. But the most important one for the general operation of just looking around and designing sensors is the thermokinetic interaction, which is, it's a function of the kinetic energy of the atoms and the molecules. And that is going to be the subject of the next few slides. But before I go on, I should mention that in addition to emission of photons, the process is reversible. So the detection of photons, the way detectors work is, again, it's back at the atomic scale, where a photon is incident upon an atom and the electrons will absorb the photon energy and move to higher energy levels within their orbits. So it's a reversible process. There's a lot of similarity between photon emitters and photon detectors. But again, back to the thermokinetic energy, the reason why that one is so important is illustrated on the next chart, which shows some of the curves for Planck's law of blackbody radiation. The blackbody is a perfect emitter of light where the frequency and intensity of emission is directly proportional to the temperature of the object. And as it turns out, most of the photons that surround us are due to the Planck's law of thermokinetic photon emission. And on the curve at the bottom there, you can see the rainbow colors for the visible portion of our light spectrum. And the big red line is for a 5,770 Kelvin temperature source, which is about the temperature of the corona of the sun. And that's why visible light is the most strongly emitted wave band of photons coming off the sun. But that's pretty hot. And then as you move to cooler and cooler temperatures, such as the solid black line, which is, I don't know, I guess about 288 Kelvin, that's about the mean temperature of our planet Earth. And you can see by the wavelength scale that there's really a negligible contribution in the visible spectrum, but there's a lot of contribution of photons around 10 microns and in that neighborhood. So maybe 4 microns, and then beyond 10 into the 20s past 100. That's pretty important. So what that means is everything on the planet Earth is emitting photons all by themselves, just because they're at a temperature roughly equivalent to the average temperature of the Earth. And that creates, that means just about everything you see, the room you're in, the chairs you're sitting on, the ceilings, everything is emitting infrared photons. And we'll go to the next slide. So again, for the Earth, with an average temperature of around 288 or 287 Kelvin, there's quite a bit of photon flux or photon emission in the infrared spectral bands around 10 microns. So this is beyond the visible. You can't see it with the human eye, but we do have detector devices that can see photons in this wave band. The little spectral plot I have here is a kind of a neat, it's an online source. It's called spectralcalc.com. I use them all the time for quick calculations. And it has various options to solve the Planck law over different ranges of wavelengths and a few other parameters that you can play with. It's very easy to use and it's kind of fun. So taking that, I moved it to using some NASA data. It turns out the average temperature of the planet Mars is about 210 Kelvin, so it's much colder than the Earth. And by running that, changing that temperature and running the same analysis in SpectralCalc, you can see that planet Mars has a lower photon output. You can see that by, if you notice the scale over here, it only goes to about 1.5 on the spectral radiance output. And the peak wavelength is now shifted to somewhere between 13 and 14 instead of 10. So Mars is much colder. That means the Planck black body curve has dropped in intensity and shifted towards longer wavelengths. Okay, so that kind of explains some of the general properties of light that we're interested in, the wavelength and the fact that materials at temperatures are naturally emitting different types of wavelengths of light. So now we're going to discuss in the next section the interaction of materials with light. And most people are probably familiar with the term the index of refraction, which applies to transmissive materials, which will generally have a very complex relationship with which wavelengths of light that they will transmit, which ones will be absorbed, and which possibly might get some other phenomena may occur. So it's interesting to see in the upper right corner there is a figure of fused silica and its index of refraction responses for different wavelengths of light. And you can see where there are spikes, that means there are big absorption bands. And then where it kind of flattens out, it means that there's a fairly decent transmission band. So that's the first property of matter, is the index of refraction, which translates into the speed of the light as it goes through the medium. And the second thing about light and matter interaction is when light passes through an aperture, so a non-transmitting edge, like a slit or something, or even the edge of a building or anything, there's always the generation of secondary wavefronts which will emit from there. And by studying the different types of diffraction effects, you can come up with different relationships for the smallest resolvable angle that's possible, and that will be a function of the diameter of the aperture and the wavelength of light. So the angle in the little formula here, alpha is your angle of resolution, lambda is your wavelength, and capital D is the aperture diameter. And then if you have multiple diameters or multiple apertures aligned together, you can get all kinds of interesting diffraction patterns. And it's the study of these diffraction patterns that led to the debate about whether light is a wave or a particle, because it shows the behavior of both. Interference is a wave-like effect mathematically. So I'd like to point out that this is an area that's still under study, and there's a really exciting new thing coming up called pilot wave theory. And it's I've got the YouTube link here on the slide, and hopefully people will have access to the slides after this talk, but it's definitely worth checking out. And the way I perceive this is, without going into too much detail on how this is done, it looks like there may be something to the concept of the ether, which was originally thought to be the medium through which light propagates. And in fact, there may be such a thing as the ether. So we'll see. There's still a lot of research going on in this area. It's actually quite exciting. Okay. So a couple of terms that get used a lot of times, and it sometimes can be confusing, is the optical path length versus the phase. An optical wave will have a sinusoidal variation, and it will be moving at the speed of light. And when the light hits a new material with a different index of refraction that's higher than 1, the light will actually slow down, and that will create a compression of the wavelengths, but the frequency will still be the same. And then when it exits the material on the other side, the wavelength will be restored back to the way it was. And the relationship here is given by it's a very easy formula. N equals N0 times the quantity of lambda 0 divided by lambda n. So this is kind of an important thing in the sense that it introduces the concept of an optical path length, and it leads to Fermat's principle, which states that the ray path that a light wave is going to take going between points A and B, where it changes from one index of refraction medium to the other, from N1 to N2 here. The path that the ray is going to take will be the path of least time. And this is a version of, perhaps, I guess it's a kind of a more general concept called the Lagrangian formulations, which actually apply not only to light, but also Newtonian mechanics and all kinds of things. It's all about the path of least energy. In the case of a light ray, least time means least energy as well. And by running through some of the Fermat principle equations, you can actually, by setting the derivative equal to 0, you can derive Snell's law and get your classic, n1 sine theta 1 equals n2 sine theta 2. But that's not even necessary. There's actually quite a bit you can do by using Fermat's principle as it is right here, and it's fairly simple, and we'll show an example of that in a little bit. And then to visualize what's happening as a light bundle of light rays comes in and hits an index of refraction change into a new medium, I always think about it as it's as if someone is throwing a book into a pool of water. So here's our green book, and it's traveling down, and then it hits the water surface, and the tail end of the book at the bottom hits first. So that's going to tip the book, and then eventually the whole thing will go into the water. This is analogous to exactly how a light ray moves into a medium with a higher index. And it's reversible, so if light rays are going the other way, the same thing would happen, is the light would speed up on the end of the book that clears out of the water line first, and it'll create the same angle. It's just a good way to visualize what's happening. The first material to consider is the Earth's atmosphere. In my world, we tend to, our main focus is on sensors, which can see over many kilometers of distance across the Earth. So the first optical material we have to worry about is the atmosphere. And as it turns out, due to the absorptions of various molecules such as water, carbon dioxide, oxygen itself has some absorptions. There are spectral pass bands that the atmosphere is pretty good at transmitting. And so we've divided in the infrared spectrum, which is starts just beyond the visible light wave regime. We have the shortwave infrared, the midwave infrared from about 3 to 5 microns, and then the long wave infrared from about 8 to 14 microns. If you remember back at the black body curve, for the planet Earth, there's not a lot of self-emission in the shortwave band. So that one's got the red color around it. It's still infrared, meaning it's beyond the red light that you can see with your eye, but there's not a lot of self-emission going on in this spectral band. So that means you need a light source if you're going to try and see something there. Whereas with the midwave and the long wave, there's actually quite a few photons out there, and you won't need an external light source. And if you're on the planet Mars, the long wave band still works, although it's getting a little dimmer, and there's really not much energy in the shortwave or in the midwave band. So that the atmosphere kind of defines what the spectral bands are that we can work with for sensors. And I should also point out down here, I'm also showing several different aerosol compounds or airborne particles, glucose, sulfur hexafluorine, various ethyls and acetones. They all have their own characteristic of absorptions. And you can design sensors that are tuned so that they can detect whether these things are present in the atmosphere. So it's a good way to find out if there's pollution in your neighborhood. And here's an example of, these are satellite views of the Earth. On the far right, we'll start with that one. That's a visible image, so that's what you would expect to see. And that's taking advantage of the visible light transmission through the atmosphere. On the left side, though, is an infrared image, probably around the 6 micron regime, which is heavily absorbed by water in the atmosphere. So what you're actually seeing is these are the different swirls of different water vapor collections all throughout the Earth's atmosphere. And you really can't see the ground through it except in a very few small little locations here. Okay. So in the world of infrared optics, it's a little bit different than in the visible light world, where you have glass companies such as Schott, O'Hara, Hoya, and there's a whole bunch of them. And there's tons of different visible glasses, and there are also plastics, and certain crystals as well are very transmissive in the visible spectrum. In the infrared spectrum, especially in the thermal infrared spectrum, where you want to have materials that transmit between 3 and 12 microns, there's a lot fewer materials that are useful to make optical elements out of. Some of the big ones include germanium, gallium arsenide, zinc selenide, and so on. And then I've marked off some of these here. The sodium chloride, believe it or not, is an excellent optical material, but it's got the same composition basically as table salt. And it doesn't work very well if it gets wet. So we can't use it in a lot of terrestrial applications. But if you're in outer space or on the moon or something, sodium chloride is an excellent optical material, very low absorption. And sometimes its index of refraction, as being as low as it is useful. There's also a material called KRS5, which uses the element thallium. It's also a salt, and it will have some dissipation in water. But this one is actually, because it contains thallium, it's actually quite poisonous. And there's some interesting stories about that, where thallium poisoning is actually something that was used quite a bit in the Middle Ages. Oh, looks like I've lost control of my slides again. Let's see, is everybody seeing a white screen right now?
Yeah, John, we can, it's showing white screen right now.
Yeah, okay, that's what I've got on my end as well. Sorry about that. There's something going on with my PowerPoints, or I mean my PDF reader here. So,
if you like, I can try to bring up my machine.
well, I'm gonna have to stop sharing for a moment here, and I'm gonna try and reopen the PDF slide. Sorry about that.
While you're doing that, I'll bring up mine too, just in case, you know. So.
All right, I got mine up. Can you see it?
Yes, we can.
Okay, so I was talking about KRS5 is an example of a material that uses thallium, which is a well-known poison. And it turns out that the antidote, if you ever do get hit with thallium poisoning, is the pigment called Prussian blue, which is what was used in the Vincent van Gogh's Starry Night painting shown here, and quite a few paintings actually back in the Renaissance era. It's literally right out of the Game of Thrones. You just take the pigment as an oral antidote, and it takes the thallium right out of your body. Interesting stuff. Okay, so we'll keep moving here. Where do these optical materials come from? Well, they come from the same place that almost all our materials come from, which is the ground somewhere. And I've chosen here, germanium is a very popular element used for infrared optics. And the U.S. Geological Survey has all kinds of resources on their internet websites. And you can get all kinds of historical information as well as current world supply status and things like that. It's kind of interesting. We're so used to, in the engineering world, you're so used to working with things written on paper and computer programs and slides like this. Ultimately, where the rubber meets the road is these materials have to get dug up out of the ground somewhere and then put through a refining process in order to get the optical quality materials that we need. So let's see, I gotta speed myself up here. So we'll go to the next slide. And here's an example. Typically how the infrared crystal materials are made. So this includes germanium, zinc sulfide, zinc selenide. The raw material is dug up out of the ground and crushed into a powder form, and then it's placed into very high temperature furnaces, well over 1,000 degrees centigrade, and varying amounts of atmospheric pressure, several atmospheres of atmospheric pressure. And by doing that, that creates it sparks the crystallization process, and then they grow these large boules of material that come out of the tanks. And then the boules are sliced up into various sizes depending on the types of lens blanks that people want. So they may be 8 inches in diameter, or they may be cut down to 1 inch in diameter. And then the blanks are cut out of these ingots of which are in turn cut out from the boules. And then those are sold as lens blank materials, which you can then fabricate through conventional polishing or other processes such as single point diamond turning and magnetorheological finishing and things like that. Okay. So I'm trying to keep things moving here. So the next section is, now that we know about the wavelengths of light, we know about the Planck's law and how thermal energy, photons in the 3 to 12 micron region are floating around pretty freely. We don't need light sources to see them. So now we want to design an optical system that will work with a detector that's designed to detect those wavelengths. So first, I'm going to do a few notes on image formation. And the basic concept of an image is that you start with your light source object, which is going to be generally emitting light in a spherical or hemispherical pattern. That wavefront, and a wavefront occurs with every cycle of the wavelength, will spread out from the object. And then over great distances, the curvature of that wavefront is ever expanding. And so by the time it gets to the location of where your optical aperture is, the wavefront will have very, very little curvature left as perceived by the optics of your sensor. That's called a collimated input, and you can tell collimated because the wavefront lines are straight up and down, just like columns on a Greek building. The optical system will then capture that light and then try to bend it back down in a converging wavefront back down to the image. So that's the basic principle of how an imaging optical system will work. And we'll go to the next slide. And so as the optical system is trying to bend all that light back down, that takes us back to Fermat's principle. In order to have a perfectly converging spherical image point, the optical paths of each one of these rays at all positions across the aperture, the optical path lengths have to be identical in order for constructive interference to occur here at the final focus point. And then that will give you your optical spot size, which is limited by the diffraction around the aperture of the element. And that's what's shown here. So the optical path lengths of these rays are the key, and the optical path difference, or OPD, is defined as the difference between, you start with the chief ray, which is right in the middle, and that's your reference. And then the optical path difference is the actual path of these other rays minus the path of the chief ray itself. So it's a differential. And this is a pretty powerful concept. And in fact, when you use lens design programs, such as software packages such as ZMax or Oslo or Code 5, this principle is extremely important for how those programs will optimize your lens system to try and achieve the best performance. So image formation in general is captured by the Newtonian Gaussian optics rules, which I'm showing here, but we're not going to go into in any detail. These rules apply under almost all conditions, and this is how microscopes are designed, magnifying glasses, all kinds of things like that. But I'm going to talk about for the imaging optics special case where the object distance is practically at infinity, which again corresponds to that collimated wavefront. So if this Z0 term here for your object distance goes to infinity, then all these equations reduce down to something much simpler, and this is your working set of equations if you're designing a lens system. So referring over here to the figure, the lens will have a focal length, which is the point at which the image comes together for you. And as a function of the image height and the incoming image angle, the focal length is really what links those two together. So if you have a short focal length, you'll get a larger field of view angle for a given image height, for example. And then the other side of the parameters here is the half cone angle of the focusing ray bundle. So there's an angle here as the light comes to a focus, and the half angle of that I've got defined here as theta. And there's a term called the F number, which is formally defined as the focal length divided by the diameter of the incoming beam, but it's also approximately equal to the inverse of 2 times the sine of this theta half angle value. F number was created a long time ago because it's an easy calculation to make, and it's not as cumbersome as working with an inverse sine function. The two are mostly equivalent until these angles get really steep. So if you're designing microscopes and things like that, they tend to not use an F number parameter. And in fact, most people will refer to F number only in the case where the object distance is at infinity. Okay. So to kind of sum it up again, on the Earth, almost all the matter that surrounds us is emitting photons in the 3 to 15 micron spectral band. So we do not need sunlight, we do not need artificial illumination to provide photons. But there's a downside to this. What that also means is that when you build a lens assembly, the lenses themselves and the housings that they're placed in and any other material around them is also going to be emitting photons as well. And so that means the only way to blacken something in the infrared spectrum is to cool it far enough down so that the Planck's law emission curve drops away from where your sensitive band is. And basically what that means is if you're operating a sensor at a 10 micron wavelength, in order to knock down all the internal emissions, you're going to have to cool those surrounding matter colder than the temperature of the planet Mars, actually. You have to get it if 10 microns is the target. Additionally, typical glass and plastic materials, as I was showing with the fused silica before with the index of refraction, they tend to absorb in the infrared band. So again, the materials that we have to use are more specialized and generally more expensive crystals such as germanium and zinc selenide and zinc sulfide. And then the other thing to keep in mind is the diffraction limited spot resolution, which, if you recall, that angle alpha, which is lambda over d, the diffraction limited resolution is a function of wavelength, and it gets worse. So you've got this kind of competing things where the longer wavelengths you go to, the more energy there is, but also the worse your diffraction limited spot size resolution becomes. And then finally, we have to keep in mind the atmosphere plays a role. If we design a sensor that sees at 6 microns, you're going to see mostly just the atmospheric water content, which from a satellite might be good, but if you're down on the ground and you're trying to see something around you, you don't want to be looking at 6 micron light. All right, so we're going to go through an example here. Let's say we have a customer who wants a long wave sensor, which would be somewhere around 10 microns, with over 1,000 pixels and a field of view of 15 degrees, which would be, if you make it a plus or minus, that would be plus or minus 7.5, assuming it's centered. The scene will be at an infinite object distance, and we have a detector that has the right number of pixels, and it happens to be an 18 millimeter format size. The format is the size of the detector. And the detector manufacturer tells us that their signal to noise ratio is pretty good around an F number value of 2. So that will be our target for the F number. This is enough information to get started on a lens design. Of course, there would be other parameters such as how big can it be, does it have to have other functions such as changing field of view or changing focus and things like that. But this is at least a good basic starting set of parameters. So we can take the information that was given in the requirements and very quickly come up with what the focal length would need to be, and that comes out to about 68.4 millimeters. Once we know the focal length, we can also then determine what the aperture diameter D must be in order to meet the F number of 2 requirement. And that's a pretty good set of parameters to get started with a lens design. So now if you think back to Fermat's principle, says the light rays that converge to a focus point all have to have the same optical path length. So if we do a thought experiment, let's say we start with just a lens blank. It came out of the ground, somebody grew it into a crystal boule, and they cut it off in a nice circular disc like this here. The chief ray is the ray that goes right through the center of the lens and ends up at our desired focal point. So I've got 3 points. D0 is where it starts in the material. A is where it exits from the material, and then B is where it ultimately comes to that 68.4 millimeter focal length that we want. So there's a path length there from D0 to A would be, in this case, I'm using 5 millimeters. It would be 5 millimeters times the index of refraction. That's the path length there. And then A to B is in air, which is an index of 1. So the optical path length is just the measured distance. If I have other light rays, I know I have to have a relatively fast F number on the order of 2, so I can calculate what my aperture height needs to be, and that's this dn up here. This ray, the red dotted line, is going to need to have the same optical path length as the axial ray down here. So how do we do that? Obviously, the way I've got it drawn here, this cannot be. The path length from DN to C is the same as from D0 to A. So those are the same. And this portion from C to B is obviously the hypotenuse of a triangle, which must be larger, or at best case, for very close to the axis, nearly identical to the path of A to B. So how do I make it so that this path length equals this path length? Well, the way you do that is shown on the next slide here, and this is this is the trick. This is how the computers actually calculate what the ideal lens curvature is going to be. So what we can play with is the sag of the lens material. We can cut away material. We keep the same height coming in because I've got a plano surface on this side to keep it a simple example. So from DN to C, that is now a variable. And then whatever's left from C to B becomes another variable. So now by pulling in this amount of material, I can change what the path length is. At the same time, down here at the center from D0 to A to B, that stays exactly the same. I'm not changing that. And just by using trigonometry, we don't need to use Snell's law. We don't need to calculate aberrations or anything. We can just use Fermat's principle and the optical path length concept to manually optimize what the preferred location right here, this point C, would be based on some amount of material prior and then some amount of air gap afterwards. It's a very simple set of calculations, which is exactly what computers are good at doing. And so I've made up a little table here. It's not something that's easy to explain verbally. But all I'm doing is calculating each of these little segments of the ray trace here. So D0 to A to B, C to B, DN to C. And then the sag value is, if I just drop down from wherever I ended up here, it would be the difference between E and A. So that's the depth of the sag. And you can very quickly generate a table using an Excel file or MATLAB or whatever, and optimize where that position needs to be in order to match the optical path length of the center axis. Once you have that, and in this case, it turns out a sag of about 0.7 millimeters came out to be the answer for this particular one to get us to the 68.4 millimeter focal length lens. Once you have the sag values, then it's fairly easy to go ahead and convert those into a spherical radius of curvature if a spherical lens is all you need. But in the world of infrared optics, because we have materials like germanium and zinc selenide with very high indices, germanium is an index of 4, which is really high. But even for zinc selenide at 2.4 or zinc sulfide, they're very strong lenses. And by using aspheric curvatures, you can actually do quite a bit of optical work with just a single lens. It's pretty impressive when you see how it's done. And that's why optimization with the optical path length is so important, because once you deviate from a spherical sag, then a lot of the aberration theories become extremely complicated, and you don't need to go there. If you stick with the optical path length concept, it's much easier and much more direct and much more computer friendly. Okay. So now I'm going to move, the next section is dealing with some of the special considerations for infrared optics. And the first one is, again, back to Planck's law. If we mount a bunch of infrared lenses inside of a housing, we have to remember that the housing material itself is also emitting photons that can be seen by the detector. And that can partially wash out a scene if we're not careful, if there's too much of that emission. So how do we control that kind of problem? Well, that gets into the tricky business of pupil control. So the pupils are the locations where the field of view angles, ray bundles, are crossing over each other. So they kind of look like focal planes when you look at a ray trace, but they're not. These are actually collimated beams crossing over each other at the pupil position. So in this upper case, I've got a simple lens, pretty much just like the one we were optimizing a minute ago. And the pupil is located right here at the front aperture of the lens, and then the light comes to the focus. So if this little line way over here on the right side is our detector, you can see that if I have a housing anywhere in this area, if it's emitting photons, they're going to go right onto the detector. And that's going to create a noise signal that will interrupt the image coming in from the scenery. So what I can do to try and limit the stray light paths is move the stop back closer to the focal plane. So this red line here for stray light is the same, it's parallel to this line here. So by moving the stop, look what happens. Now, in order to get through the pupil, it has to come through at an angle where it's going to miss that focal plane. So now all I have to do is make sure that the area around the focal plane up to the stop is cold enough so that it's not emitting, so that this area is not emitting any photons. And that will help solve the stray light problem enormously. The downside of doing this, however, and you can see the way the rays are now spreading out from the pupil. Remember, the pupil is where the fields of view all cross over each other. If I make that crossover point back here, they're going to be spreading out at a much larger angle than they were compared to here. And so now my lens isn't big enough. It's not large enough to capture all the rays. And you can also see from the ray trace that the aberrations, especially spherical aberration, that's starting to play a much larger role. So while this is a good thing to do for stray light rejection, it makes it tough to keep the size of the elements down, and it also makes the aberration correction a lot more difficult. So there's some drawbacks. And this is really the key to a lot of infrared optical systems, is dealing with this problem. So in that area around the focal plane, what we'll do is we'll create a kind of like a little wraparound cavity called a cold shield. And we will generally cryogenically cool these. It's got to be colder than Mars, and typically liquid nitrogen is pretty widely available, and that cools it down to 77 Kelvin or somewhere thereabouts. And that's cold enough where if this is cooled to 77 Kelvin, it won't be emitting any photons that the detector can see. And then by having that made up with the optics, then that means most of the light reaching the detector is going to only be that light which is coming from the scenery outside and not from inside the device. There are still some risks, however. In a multi-lens system, every lens will have a very small component of back reflection. And in the infrared world, we use the term narcissus for that. And the back reflections also have to be managed in an infrared design. As a general rule, what you want is, if there's a back reflection occurring from a surface, you want it to be very out of focus by the time it gets back to the focal plane again. And the way stray light analysis goes, or ghost image analysis goes, is you have to look at each surface as if it were a mirror and follow the light rays and see where they come back. And this is probably the second most important thing in infrared optical design, is dealing with this issue. So you have to trace the light rays backwards and see where they go. So a typical solution for a thermal band infrared imager then is to have the aperture stop, the hard limit to the pupil size, in the back, somewhat close to the focal plane, maybe an inch, maybe 2 inches away. And then in order to control the light rays as they go through the rest of the system, the re-imaging form here is pretty popular. So you have your focus, your pupil, and then an intermediate focus, and then the entrance pupil is the image of the actual stop, and that's projected outside or up to the front lens of the system. So the re-imaging solution is a very common thing in modern infrared optics. And it's unfortunate that you need different, you need lenses to recreate the focus and then unfocus again. But having all these surfaces allows you to correct for the aberrations that come from having the stop so close to the focal point. Okay. And then for the, I think this is my last trick, is one of the issues that really pops out in an infrared design that you might not encounter in typical visible designs is that the infrared materials have what's known as the dNdt parameter, which is the variation of index of refraction with temperature. And the dNdt values for infrared crystals tend to be quite large, especially for germanium. So what that means is if the index of refraction is changing over temperature, an optical system built out of these materials is very likely to go out of focus very, very quickly with only maybe a 10 or 15 degrees centigrade temperature change. And that's not desirable. So certainly there are methods of adding a motorized focus device so that you move the spacing between the lens and the detector. So that's a possibility. But for smaller optical systems where you don't have the size, weight, and power available, there's also a technique called passive athermalization. And so what we do in a passive athermal setup is use materials with material coefficients of expansion in a way that they will offset the optical index change with temperature. And at first, when you first look at it, usually what happens is as temperature increases, the lens index will also increase. So what that means is the focus will move from the detector. It will start coming in closer to the lens. So that means if you were to physically refocus the lens, you would have to bring the lens in closer to the detector. But most materials, when you look at their linear coefficients of expansion, or DLDT, most of the materials available get longer when the temperature goes up, which is kind of going the wrong way. So one of the tricks that we use for infrared systems design is what I'll call a double back technique, where I have it with this darker blue material that will have a very high coefficient of linear expansion with temperature. And we use this double back kind of arrangement so that as this material grows with temperature, it pushes against a spring, not shown here, and closes the gap, and will actually bring the lens in closer to the detector, which is what we want. And this technique is very effective and is used in all kinds of both large and small infrared optical systems. It's pretty effective, and let's see. All right, so that kind of brings me to the end. Flying through this in a hurry here. But what I've tried to show were some of the topic areas that are unique to infrared optics, which is the Planck law, the black body radiation, and the fact that infrared light sources are all around us day and night all the time. That makes it a very fun spectral band to work in. And then given that, we can look at basic design principles using optical path difference based on the Fermat principle. Can design all kinds of neat shapes of lenses where you can correct for all the aberrations with a single surface potentially, depending on the requirements of the system. And we don't need to draw all the way back to Snell's law or aberration theories and things like that. And in fact, most lenses today are designed by using optical path difference operators in the software. And so on this page here, just to give a quick list of some resources, most of the figures that I've shown here were generated either with KDP2, which is an open source optical ray tracing software, or the mechanical things were done with FreeCAD, which is an open source solid model generating thing, kind of, I wouldn't say equivalent to SolidWorks, but it's in the same category. And for heavier calculations, there's a program called FreeMat, which is an open source version of the core elements of the program MATLAB. With these three things, you can actually do quite a bit of engineering analysis, and I've been using them for years quite effectively. It's kind of neat. So hopefully that leaves you with a little something you can take advantage of later on. Okay, that's the end of my talk. I think I've been able to squeeze it in just about on time. Sorry for having to rush there. But hopefully this was something a little different, maybe some things. My intent was to cover some topics that you might not see in some of the more standard optical classes, educational things going on. All right, I will stop sharing. And Ron, if you're there.
Yeah, I'm here, John. Let's thank our speaker.
Yep.
Okay, we've got time for a couple of questions. If got a question, Stan, got a question back here.
What do you use for AR coding?
John, the question was, what do you use for AR coatings?
Yes, AR coatings, thin film coatings are placed generally on the optics because they have such high indices of refraction. That means the Fresnel losses are also very high. So infrared coatings are very important. And some of the materials that I showed on the material chart are used as coating materials in addition to optical substrates. So that would include zinc sulfide especially. Some of the fluorides can be used, yttrium oxide. There's a whole family of crystalline materials that make for excellent durability and adhesion to the crystalline substrates.
Great. Any other questions? We've got a question down here.
Have you encountered cases where it's necessary to do active cooling on the lenses? And does this cause like thermal variations within the lens that you need to compensate for?
Generally, I try to avoid getting into that situation in the first place. There are cases, however, especially for front windows. If you're in a high-speed application through the atmosphere, there's a lot of friction. And what can happen in those cases is the window will start to heat up. And as it gets hotter, even though it's nominally a transmissive material, it does start emitting photons in the passband of the region that you want. And in cases like that, yes, it is important. Eventually, you get to a point where you do want to provide an active means of cooling. But generally, that also means the way you cool is you've got a larger bulk material. So how do you can't just cool on the edges. You have to run cooling conduits across the whole area of the element. And so sometimes maybe a good way to think about that would be something analogous to the rear window defroster on your car, where you run metal lines across the element. In a defroster, you're gonna run a current through the lines and heat them up. In a cooling system, you can use heat sinks on the outside and draw heat out that way. It's a kind of a reversible process.
Great. Any other questions? One more, John. We got one more question.
Sure, that's fine.
Hey, John, just wondering, is there a standard like low emissivity material that you usually choose for the lens housings?
For the housings, most of the materials end up more for cost and workability reasons. Most of the time, you're going to end up with aluminum or anodized aluminum, to protect it against moisture and things like that. Sometimes certain plastics are used, but they're all going to be emissive, basically. And so that's why we spend a lot of time creating the either the cold shields or reflective shields and things placed very near the detector, and then we control the progress of the light rays through the rest of the system, so that those housing materials, even though they're emitting, we design the system so that they any light rays generated by those materials can't get to the focal point.
Okay, let's thank John one last time.
Thank you.
Hey, John, thank you so much. We really appreciate it. And, you know, the infrared footprint here, your talk was a real contribution to that today. So thank you so much.
Oh, you're welcome. Well,
Thank you, guys.